All right, so now that we've played with this contraction approach a little bit, let's actually step back and actually properly present the specific algorithm. So I'm going to refer to this thing as the quote unquote simple algorithm because it's supposed to be something that is blazingly fast to do so that we can do it a bunch of times to hopefully get this chance of success. I've also referred to it as option 1, indicating that there might be a few other options coming out later, and you'll actually see those at the end of the notes. Basically, there's a small little refinements that we can do to possibly speed this up a little bit as well. So the initial presentation then is exactly the game that we just got done doing. You give me a graph, I'm going to begin contracting these edges over and over and over again until I'm down to 2 little nodes. So pick an edge purely at random. So I have no essential kind of foresight into what's actually going on. So you pick your favorite edge. I'm going to contract that thing, and I'm going to kind of take those 2 little end vertices that are going to be glued together to become a new one. I'm going to have all of the resulting kind of new little edges, and I'm going to keep that process going over and over and over until I'm down to 2 nodes. Once I'm down to 2 nodes, I can then record the number of edges that are between those things, because we know that those edges are then going to be corresponding back to a specific cut. So there's a couple little nuances that we should be chatting about a little bit before we kind of rip open the can of worms and see what all lives underneath it, is that when I do this little contraction, so if I connect, let's say B and C together, well, you might initially be like, okay, I'm going to have a vertex A, I'm going to have a vertex D, and now I'm going to have a new one, which is going to be called BC. BC is going to then be adjacent to everything that B was adjacent to, as well as everything C was adjacent to. So I'm going to have a double connection to A, and I'm going to have a double connection to D. And that's what I want to view this thing afterwards. Depending on how you go about actually coding this thing up, you might actually see little loops like that emerge. And that would emerge by, if I were to merge B and C together, and then ask, okay, well, what was B adjacent to? Let's make this little vertex then adjacent to it. Well, B was connected to A, B was connected to D, and B was connected to C. So that may create a little self loop. Same exact thing is going to happen on the C side, is that C was connected to A, D, and B. So you'd actually end up getting these little self loops. So if you run it like that, we're then going to have to go back and kind of snip those little self loops off, because I want to end up with something that looks like this. That's normally not how people actually go about implementing them, is that when you design the thing, just don't put the self loops in. Basically, you're removing that edge BC, so then when you begin kind of creating the new connections, I don't have to worry about actually the adjacency between B and C. So I'm never going to have those little self loops ever be an issue. But it should be something that is at least commented on, because if you add in those little self loops, it might throw something off when we actually begin counting edges between things. So don't have them, then we don't have to worry about it, and everything is great. If you want a couple extra little examples, so here was our first kind of toy example where I didn't go through the entire kind of snipping process. We just looked at it and said, okay, well, there's multiple cuts of size 2. So now if you hit it with this nice little simple algorithm, you can see if you get lucky or not. So here it looks like I initially did this contraction on the edge between A and B. So I'm going to move A up to B. So I create that little double edge between A, B, and G. Then I merged F into E, which was an easy process. Then I merged G into AB, which didn't actually create a ton of new stuff. Then I eventually moved D down into EF. And then lastly, I merged C and A, B, and G together. So if you look at the end of that, we end up having our 2 vertices. So I'm going to stop, and I'm going to count the number of edges between them, which is 3. And you can then see that that's going to create a cut of size 3 in our graph. I have one region, which is going to be called A, B, C, and G. So that kind of top left area. And then I'm going to have another region, which is D, E, and F, which is that bottom right. And they are separated by 3 little edges. You would then run it a second time, let's say. Do that contraction process. I'll kind of let you read through that on your own, because you're probably bored seeing the contraction process over and over and over again. And if you do this one, you can actually see that at the end of the day, I'm going to have a region called A, B, and G, which is that one. And you're going to have a region of C, D, E, and F, which is that one. The number of edges that are connected in my little tiny graph on the right is 2, which is telling me that my big initial graph can be ripped apart in 2 cuts as well. And that's the game that we're going to play, is that we have this really fast, simple algorithm that does contract, 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 contract until you're down to 2 little vertices. And then it's going to return what that cut size happens to be. You might be happy with that particular cut, or you might hit go again, and then go again, and then go again, and go, 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 and then ultimately record whatever the smallest cut size was that you found. So if you ran this one twice, you'd have initially a cut size of 3, and you'd be like, okay, cool, can we do better? And then you're going to go again, and you find a cut size of 2, and you're like, cool, that might be optimal, but maybe I could keep on going. And that is the big goal for us, is that when do we actually stop that rerun process? At what point in time are we maybe going to have a decent chance of success? We're keeping track of our smallest cuts that we've found. Are we happy with that one, or do we keep on going a little bit farther? So at this point in time, it's then worthwhile to kind of step back and say, okay, you give me a graph of, let's say, I don't know, 10 vertices. So it makes my life a little bit easier. This particular one's got 7, but 7's a tricky number to multiply out a little bit. So let's go with 10 because I can multiply by 10 a whole bunch of times. So if you start with a graph with 10 vertices, and if you were to run this straight up simple algorithm, think a little bit about what type of success rate you would be happy with. So a single run, 10 vertices, 1 run, it's going to give you a cut. Then the question is that cut optimal? Is that cut minimal? And with what probability would you be happy with that occurring? So with 10 vertices, it's pretty bad. So the chance of failure or the chance of success are going to be right around 1% and 99%. So we're going to have a 1% chance of success if I'm dealing with 10 vertices. In general, my chance of success is going to be about 1 over n squared. So if n is 10, it's 1 over 10 squared, or about 1 in 100. So my chance of failure is then going to be about 99 out of 100, or about 99%, which is not so great. But the key thing here is that my chance of success is non-zero. It's bigger than 0. So there is a chance that it will actually kick out something good. And we saw it on a couple of these little toy runs. Initially, it kicked out not successful, but the second one, it did kick out successful in that I made it work, but it would eventually kick out something successful. And that's key, is that there is a version of this contraction algorithm that will give us the optimal cut size. We just need to click go enough times until we actually find that thing. It's worth mentioning a couple of little comments down below before we kind of really go into the nitty-gritty of these things. This simple algorithm is really, really fast. If you go back here and we had a graph that had, let's say, 7 total, nodes or vertices, we had to do this contraction only 5 times. So we went from 7 to 6 to 5 to 4 to 3 to 2, and then we were done. So the simple algorithm is blisteringly fast in that if you give me a graph that has 1,000 nodes on it, I'm going to have to only run that contraction process 998 times, which is really fast. It's not an expensive operation to do. It's just going to be like, and then you're done. Way faster than trying to kind of be like, well, what happens if I cut this? And what happens if I cut this? And do all that kind of weird, problem solving side of things like that. I'm just going to be like, okay, randomly grab edges and then let it kind of go all the way down to 2 things and then record the number of edges that are going to exist between them. So that's the key thing, is that this simple algorithm is really, really fast. It's very nice to work with. So then the idea is that even though it's got this very small chance of success, the trade-off is that it's so easy to compute, I can just run that thing a whole bunch of times, just over and over and over and over and over and over and over again. So if you think about, let's say a graph that had 1,000 nodes on it, you might think really badly about this chance of success because my chance of success is then going to be like 1 over 1,000 squared. So we're looking at something like 1 in a million chance of success. Well, then the idea is like, okay, just run that enough times and eventually that chance of success might pop up a little bit. And you're like, well, I just run it a whole bunch. But the trade-off is that that whole bunch of runs is still way better than actually trying to go through all of the possible combinations of edges of being like, well, if I remove that one, that one, that one, and that one, so if I remove these four, then what happens? So if you think back to a graph of about 1,000 or so nodes, if you have that one super duper dense, you could have somewhere around the lines of about 500,000 edges. So the total number of ways that you could create clever little combinations of edges to possibly be a cut would be something like 2 to the 500,000, which is astronomically large. Then the idea of running this simple algorithm 1,000,000 times no longer seems so problematic, is that I can run this really fast process 1,000,000 times and it's going to dominate otherwise this kind of going through 2 to the 500,000 number of possible combinations. So it is significantly faster. It's just got this of like, it may not work out perfectly. So that's the key thing here, is that it's a blisteringly fast process that we're going to run enough times to then dwarf the kind of brute force approach. And it's a really cool thing, is that we're going to kind of boost this thing up over and over and over and over again. And then we're going to return something back to the user that's super duper nice and tight. So I'm probably going to pause it there, and I'm going to go into a little bit more of the technicality of it in the next video. But at this point in time, it's probably running kind of long. So I'm going to pause it there, and then we'll jump back into the goodies.